All right, and we are back. As promised in the morning. So let's look through 4.4 today, or this time. So weird actually giving like lectures and stuff like this in this format because in some sense there's no days, right? There's no days and nights. There's just 1.5 to 2.5 hour segments of time that I'm on camera. So, sorry, weird philosophical ruminating for the moment, but okay, good. So let's, we want to look at 4.4. So in 4.3, introduced a new definition, what do you call it? Rational numbers. In 4.4, I want to introduce another new definition. So in 4.4, you read through it and you worked through the reading. She introduced the idea of divisibility. So one number, the ability of one number to divide into another, basically. So kind of as usual, the first several reading exercises are just about you getting comfortable with the definition of divisibility. So not only again with maybe what you have thought that meant before, or just getting, the math that you've seen before, the math that you do in your head, the intuition that you're comfortable with, whether one thing divides into another. But we want to get comfortable then with, so that's ambiguous. So we want to nail down a definition and get comfortable with that definition. And then we're going to use that definition to do our proofs. So the first four parts of the reading actually were all about just getting comfortable with this definition. So I gave you 1 through 4 as the first part of the reading. So let's start with 1. The question was, is 52 divisible by 13? And you guys said, good, yes. It's obviously divisible. So again, calculation-wise, it's obviously divisible. But what shows that it is divisible? So this is, and I think she actually wanted you, did she want you to give a reason for each of your answers. So this is a yes, but the reason is because we have 13 times what? 4 equals 52. And the key here is this. Key is the 4. So the key is the fact that that's an integer. So to say that one number is divisible by another means that that other number, when you, what do you call it? When you multiply it by an integer, gives you the first number. So I don't want to get into, actually I don't want to get into a ton of like first and second designations, but to say that 52 is divisible by 13, what I'm saying is I have to have an integer so that 13 times that integer equals 52. That's the key. And that's what we do in our head. So you told me that it is divisible because in your head you searched it out, or maybe on a calculator you searched it out and you figured out that 13 times 4 is 52. Good. So that's our key. To say it's divisible means there's an integer that I can identify. That 13 times that integer gives me 52. So then in 2 is asking the exact same thing, but it does it using symbols rather than a sentence. So number 1, I want to bring up kind of how these things are being written. But especially in this section, I want to bring up how they're being written. So there's a decent bit of vocabulary and just kind of syntax here. So in the first one, is 52 divisible by 13? That's how they said it. So they said it as a sentence. The 52 came first and the 13 came second. Here they're asking, does 7 divide into 56? So they're asking the same thing. They're still asking, can you find an integer where 7 times that integer gives you 56? But notice that the order on the numbers is reversed. So kind of the number that you're dividing by actually comes first here. And so that's the way you want to read this syntax, this symbol, this language, is this reads as 7 divides 56. But the question is still, does 7 divide 56? And that's a yes, because 7 times 8 equals 56. And again, key here, sorry. Write this in. This was an integer. Key here is the 8, the fact that that's an integer. Okay. The first three here are just numbers. So we want to get to the point like we saw in the last section. We want to get to a point where we can talk about divisibility when we're dealing with variables. Because when we go to do these proofs, we can't prove things out of examples, right? So we can't prove things out of certain numbers. We have to prove things out of generalities, and generalities are always written in variables. So we wanna get there, but one more. Does 5 divide into 0? And that should have been a yes as well, because 5 times 0 equals 0, and 0 is an integer. So then the fun one. So they're asking, does 3, so in the way they word it here, they do it as a sentence. But they could have written it this way. So they could have asked the same thing by writing this. Does 3 divide, and what is it? 3k plus 1, 3, yeah. Does 3 divide 3k plus 1 times 3k plus 2 times 3k plus 3? And so again, like I said, we want to, so this is fine enough and easy enough when we're thinking about numbers, because again, we've been in a bunch of math classes where we use math as a tool. So we've been playing with numbers our whole lives. And so this is all not even just intuitive, but you're just kind of like, okay, that's arithmetic. That makes sense. But what I want you to notice is, on something like 4, whatever k is, 3k plus 1 times 3k plus 2 times 3k plus 3, that's an integer. And 3 is an integer. So I can still ask the same question on something that's an algebraic expression rather than just a number. I can still ask, does 3 divide this thing, even though I don't really know what that thing is. That thing really is just a construction involving k that, we could multiply that out and make a nice little polynomial, standard form of a polynomial for it. But ultimately, it's just, it's an expression, it's a function, it's an equation. Well, not an equation, but it's an expression or it's a function. But it represents an integer just as well. So we don't need things to be numbers. In fact, again, when we get to these proofs, you'll see that's what we're trying to get to, is we're trying to prove things about divisibility. Trying to prove things about divisibility in general, on general expressions or some general for all if then statement that we want to prove, rather than on specific numbers, because we don't need to prove it on specific numbers. We've been doing that all our life. So anyways, so does 3 divide this integer? And what did y'all say on that? And so maybe you had an answer for this, or maybe you kind of looked at this and said, you know what, I don't know. Or how am I supposed to figure out if 3 divides something like that when, again, it's not a number? So I want to go back again to what we saw in 1, 2, and 3, but I want to summarize not the numbers, but I want to summarize how we knew things were divisible. So we knew that 13 divided 52 because 13 times an integer is 52. We knew 7 divided 56 because 7 times an integer is 56, etc. The same for 3. So we know one thing divides another if that one thing times an integer gives you another. So, and that ends up, that's not only the idea, but that's actually the definition of divisibility. That's the definition that she gave you guys in the section. But that's what we really, not just that she's giving you a definition out of the blue, right? That's what we really mean. When we say one thing divides another, we mean that I can find an integer where the one thing times that integer gives me the other. So that is our definition of divisibility. And let me actually try to write that down somewhere. So in general, we want to say, I should have wrote that lower, but that's okay. So in general, we want to say, so definition. We want, in general, we want to say A divides B. Is this an if and only if? Yeah, it's an if and only if. If and only if A times K equals B, where K is an integer. So really all these are well, yeah, all these are integers. So A, B, and most importantly, K being an integer. So that's how we can tell if one thing divides another. And notice that that definition kind of succinctly in your head, or maybe it's hopefully it's doing this in your head. It succinctly collapses down a lot of ideas and calculations and terms we've used before. So again, I'm saying A divides B if and only if A times an integer equals B. So that means that A is a factor of B. So when you factored something out before, that's what you're looking for is A times an integer equals B. At least when you factor, what do you call it? Numbers. When we factor polynomials, technically, yeah, you still end up with the same thing. But when you factor polynomials, you're really looking for expressions that divide into it. Anyways, but so that takes care of factoring that you've done before. So factoring means the same thing as dividing. So A divides B if and only if I can find some integer where A times that integer equals B. So that takes care of, again, factoring that you've seen before. It takes care of when you say one thing is divisible by another. It takes care of just kind of sort of, there's a lot of words that we've used and again, in our trail of mathematics, going all the way back, honestly, to probably third grade or so, or whenever he started learning about multiplication, second grade, third grade. There's a lot of little terms that they've been using, and they all actually mean the same thing. We've the whole time from third grade on, when you've been trying to figure out, if one number can divide into another. So that's another, we say one number divides into another, or if one number can be divided by another. That's always what we've been doing is we'd start out by using our multiplication charts and go look for an integer that works. And then, yeah, I mean, actually that's, and then you just kept doing that as you went up through classes. Good. So I guess the point I'm trying to make, I'm kind of, I think, losing the point I'm trying to make. I think the point I'm trying to make is that this has always been what dividing it has been, or divisibility has been, or factoring has been, etc. This is actually always what you've done. All you've ever done is look for an integer, so that you take the small number times that integer and you get the large number. So we're just taking that thing that you've done, that and make that, that process, that idea, and making it a general definition. So A divides into B if and only if I can find some integer K where A times K equals B. Good. So back to 4. So again, back to the question of, so how do I've done this with numbers all my life. How do I do this with something general like this? Well, I still am just looking for an integer so that 3 times that integer gives me this whole expression. So what you might notice here, so the answer to this ends up being yes. Oh, man. But let me kind of give, I guess, the prep for where I get that answer. So what you might notice here is that this last term can be factored. And that factoring is 3 times K plus 1. And notice that then this integer, this number, this expression can be thought of as 3 times a k plus 1 times the 3k plus 2 times the 3k plus 1. But more importantly, is k plus 1 an integer? Yes, because k is an integer. So we know that the sums and products of integers are integers. So because k plus 1 is an integer, 3k plus 2 is going to be an integer because of the sums and products of integers, and 3k plus 1 is also going to be an integer. I now have 3 times basically an integer because I got integer times integer times integer. So I can rewrite that expression no matter what k is. It actually doesn't matter what the number is. So again, a little bit like we were talking about in the last lecture, it actually doesn't matter what the number is, and that's the way we want it. That's the better way. No matter what k is, I can always rewrite this as 3 times these 3 integers multiplied by one another, and 3 integers multiplied by one another is an integer. So I can always rewrite it as 3 times an integer. And then bingo bango, that's the definition of divisibility. So if I can represent or rewrite or express this as 3 times an integer, then I've got it. 3 divides into it. And again, the beautiful thing is it doesn't matter what k is. I actually don't need that kind of detail or specificity. The abstract is actually better here. I need it to be an algebraic expression. I need to do factoring instead of thinking about numbers. So that's pretty much the justification here. So you would say yes. Oh yeah. So let me rewrite this out. So we can say 3k plus 1. Actually, so I can say 3 times 3k plus 1 times 3k plus 2 times k plus 1. That actually equals, that's the same as the expression we're starting with, 3k plus 1 times 3k plus 2 times 3k plus 3. And notice that the way I'm writing this out is starting to look like our definition. So again, the way the definition I have up here, if to say A divides B, I need to show that A times an integer equals B. And I do have A, so I'm trying to show that 3 divides this. I do have A, and I do have B on this side of on the other side of the equal sign. So now I just need to show the reader that this is an integer. And it is because of sums and products of integers. So I'm gonna not really shortcut it, but I'm gonna say we can kind of see that each of these individually, like I just mentioned, is an integer because of sums and products of integers. And then I'm gonna multiply those 3 integers together. So the whole thing is sums and products of integers. So we can say 3k plus 1 times 3k plus 2 times k plus 1 is an integer, and that's because of the sums and products of integers. And that's what I need. So again, I need to show the reader that there is an integer, that 3 times that integer gives me this expression on the right. So again, when we go to a proof, we'll go to a proof in 14 and then go to our writing our own proofs. But when we go to a proof, these are the parts that you're going to start to see. So if I need to justify that this is 3 divides that, then in the middle of the proof, kind of the meat of the proof, I'm going to say something like this. I'm going to show the reader, just make the observation that 3 times that equals my B. And then I'm going to have a separate line that says, hey, these are integers and their products are integers because of sums and products of integers. And then we might say at the end, therefore, 3 divides this, this thing. So this is the key. This is what we'll be working with all day today. Yeah, give me just 1 second. I'm gonna pause the video. You guys won't see it on your side because it'll just keep rolling. All right. Now maybe pull this down, but all right, sweet. Good. So we now we know a divisibility. Again, instead of an ambiguity about it or just thinking in our head, oh, one thing is divisible by another, we now know exactly what it means. And like I said, it's kind of the thing you've actually been doing all your life with divisibility. You just never really thought of it as, oh, I'm finding an integer, and this thing times an integer gives me another integer. But that's what we've been doing. So we now have it succinctly, exactly. And like I said, 4, hopefully, I felt like I was talking and way over talking through it. But 4 hopefully gives you an idea of how we're gonna then play out divisibility in these proofs. Because again, in the proofs, we want to prove that things are true for all integers that that this applies to. So we can't prove it like we did in 1 and 3 for one integer, because that's just proving from an example. We need to prove it. We're going to use elements of what we did in 4. We need to prove it like we did in 4 for all integers, like this would have been for all integers k. So a good example of that. Let's go to 14 that I gave you guys for the reading. I do want to keep that up there though. Yeah, let me erase. So let's take a look at this fill in the blank proof that she has going here. So in this one, she wants to prove that for all integers a and b, if a divides b, then a divides negative b. So again, for the reading, you didn't have to write this up here, but I do want to write this up here so that, like the last section, it can really emphasize, we can really look at, again, everything you're going to try to prove, if you can, if it's not already written as an if-then statement, you want to think of it that way, or even write it down for yourself that way. So what we're trying to prove, she's saying for all integers a and b, if a divides b, then a divides negative b. And so basically what we're saying here is if a divides another integer, then it divides the negative of that integer, which again makes intuitive sense. But intuitive sense is not a proof. So let's prove it. And so notice she starts out again with the if part. So again, we're always going to start direct proof with the if part. So she says, suppose a and b are any integers such that, so part A here would have been a divides b. Yeah, we've seen the same setup in the last 3 sections now. So we saw proofs where it would say, suppose blah, blah, blah are rational. And so your first thing is, again, suppose such and such is a rational number, or suppose such and such is an even number, odd number, prime, composite. That's what we saw in 4.1 and 4.2. So we now are she introduces 2 actors, A and B, and with a specific condition that A divides B. Again, just like the last 3 sections, so if you say something's even, that means you have a definition for even. So there's some detail about that thing that you can write. If we say something is rational, there's a definition for rational, and we can write that. So if we say that A divides B, then her next step is going to be to write details about A divides B based off of our definition. And that's what she does. She says, by definition of divisibility, there exists an integer r such that So she's saying R is the integer, basically, that A times R equals B. So it kind of fits that definition there. So that's what you would have said here, such that A times R equals B. You start with your suppose. The suppose usually gives you a definition. So then you write out some details from that definition. And then once we have details from that definition, or in previous proofs, we've seen like you'd introduce a construction. Yeah, so once we have details from that definition, the next thing is we usually introduce the construction that we're worried about, the thing that we want to prove something about. And so notice she does the same thing. She says negative B equals negative AR. And then she does a little factoring, a little algebra there, and says that's A times negative R. Again, my goal, so from here, once you introduce the construction, the rest of this proof is kind of working towards the goal of the proof, which is the then part. So I want to say that A divides negative B. But to say that A divides negative B, what do I need to show? Kind of like we did in 1, 2, 3, but especially 4, what do I need to show to the reader to say that A divides negative B? Good, I need to say that A times an integer equals negative B. So that's kind of the meat of this proof, and kind of the crux of this proof is once I introduce negative B, I need to be able to manipulate that till I have A times an integer. Just like when I, here, even though again, this wasn't a full formal proof, but this would have been the meat of it. I algebraically manipulated this so that I could confirm it was 3 times an integer. And it was 3 times a bunch of other stuff, but all that stuff I could, because of sums and products of integers or integers, I could tell that it's an integer. So she does the same thing here. Her little manipulation is very clever, just quick and clever. Negative B equals negative parentheses AR, but then we can just do a little factoring there, and that's the same as A times negative R. So then she says, let T equal, so this would have been negative R. Then T is an integer because negative 1 times R, because T equals negative 1 times R, and both negative 1 and R are integers. So again, she does that thing she did in the last section where she doesn't say because products of integers are integers, she just shows you, hey, this thing is a product of integers, and they're both integers. And then that's enough, because obviously the reader can get it from there, that, okay, I'm multiplying 2 integers, I got an integer. Thus, by substitution, negative B equals A times T, where T is an integer. And so by definition of divisibility, A divides negative B, as was to be shown. One thing she did in this proof, so in the last section I was talking about, she was doing writing the proof a different way, very intentionally, or just writing some sentences differently, very intentionally, to show you guys that it can be written. You can write it a little more formally, a little more informally, but also to get you comfortable with that. That however informal or formal you want to be, you still need to make the correct pieces of the argument. So notice here she does a little thing where she says let T equal negative R. So she kind of basically, this negative R part, and I don't have it up here, but this negative R part of the construction that she factored off, she gives it a name, basically. She gives it a cute little name. She calls it T. And she uses that then as her way of writing these sentences that say, well, this thing, basically, ultimately, this thing, T, is an integer. So she didn't do that in the last section, though. In the last section, she just commented about the construction or the whole object and it being an integer. So you can go either way. You'll notice on my proofs, I tend not to do that. I kind of, lines like that where it's like let T equal the thing that I already see in the proof, in this case, the negative R, I feel like it's just, what do you call it? It's just redundant and a little bit of overriding. But also it's, I think, the way that when I read through things, I'm looking for a quickness and efficiency, simplicity and narrative. And I feel like a sentence like that gums it up. For others of you, though, when you write it, honestly, it may be the opposite, where you feel like you really want that sentence and need that sentence because it almost fills out the space in the argument there. So if you like that sentence, keep using that in your proofs. That's a very, what do you call it? I don't know. It's just a very common and useful way to sort of identify these pieces that the reader is seeing in the proof. And again, for you, it may fill it out in your head, like kind of like you feel like there's not something missing there. But if you don't like that, like me, if you don't like that and you feel like it's overly crowded and not efficient, then you actually don't need that sentence. You could have just said something like, yeah, I mean, you literally could have just said something like, negative r is an integer because negative r equals -1 times r, and both -1 and r are integers. So you pretty much could have done the same thing with negative r instead of t. So just know that you could write it either way, and whichever way feels more comfortable to you. So again, but what you're going to see, she's going to keep doing this in every section. She's very intentionally writing things in a slightly different way back and forth so that you know that, one, again, you're comfortable with different ways of reading it, but you also know that both ways of writing it are correct. There's not a one correct way to write these arguments and sentences. You just need the right elements. You need the right parts of the argument. So that's why when I'm kind of going over these proofs, I keep emphasizing start with your suppose, and then use your definition to tell me more detail, and then introduce your construction, and then prove kind of the end point from there. That is a direct proof, like what I just outlined there in words, and you can write that on your paper and block it out, or if it just makes sense, if you already kind of took a photo of that in your head, that is a direct proof. How you write those sentences is completely up to you. It can be as informal or as formal as you like, and it's gonna read the same to me, but it's gonna read the same because you're still making the same truthful argument, the same true pieces. All right, good. So a good example proof. Let's turn that into our own proof. So the next problem I want us to look at then, yeah, and give me a second because I was sort of debating this before I turned on this video. Okay, well, let's start with 15 actually. Start with 15. So 15, I would say it's probably the most, when I say basic, I don't mean like basic, easy. I don't mean like, oh, you should easily get it. I'm just saying this is the most foundational. I guess foundational is a better word. Probably the most foundational proof we could do once we have the definition of divisibility. So in 15, we want to prove for all integers A, B, and C, if A divides B and A divides C, then A divides B plus C. And before I even write the statement up there, I want you guys just take a second and tell me, so what is that trying to say? Again, so tell me informally, just brass tacks, what are we really trying to prove here? So what we're really saying basically is, if I have one number that divides two other numbers, then I want to prove that that one number divides the sum of those two numbers. So if A divides B and A divides C, it should divide their sum. Because in some ways, again, if A does divide B, then I'm saying A is a factor of B and A is a factor of C. So there's some, A then should be a factor of B plus C. There's some number of A's that should then go into B plus C, because B plus C would just be a certain number of A's for B plus a certain number of A's for C. Yeah, so that's what we're trying to get to. Okay. So then the second thing is, again, before you try to prove this, does this seem plausible? So, and to note again, I mean, this 15, she does just say prove it, so that you assume it's true, but in general, you'll see the other problems we're gonna look at after this. She's saying could be true, it could be false. So if it's true, prove it true. If it's false, give me a counterexample. But you know, again, we're looking at these problems where she's not going to give you a lead either way. So just like we were talking about in the last lecture, you want to think about, does this seem plausible? And what do you guys think? And at least to me, it does seem plausible. It seems like if A divides B, then in some sense, B is just a certain number of A's, right? And if A divides C, then C is another number of A's. And if I add the two together, then I should be able to add the number of A's together. So it should work. So because it seems intuitive to me that it should work, I'm going to try to prove this is true. And let's see where it gets. So I want to prove for all integers A, B, and C, if A divides B and A divides C, then A divides B plus C. I will say she tends to write parentheses around this. And I think she does that because when you look at this, kind of hard to tell if this is saying A divides B. So A divides B and then plus C is just separate versus A dividing this B plus C, the sum. I think also though, whatever comes after this, it kind of makes sense that it would be what you're dividing into. But I like kind of what she's doing with parentheses, so I'll put it there. Gives a little clarity. So notice this is naturally written as an if then. So I'm gonna go to try to prove this. And so, like I said, the first thing I'm always gonna start out with then in a direct proof is I'm just gonna suppose the if. Essentially gonna copy paste that. Suppose A, B, and C are integers. So my specific conditions here are A divides B and A divides C. So that is always the first part of my direct proof. And the first part of my direct proof usually gives me some piece, in this case, some relationship, some condition between A and B and A and C, but it usually gives me a definition that I can work with. So I introduce these characters. These characters are related using the definition of divisibility. A divides B and A divides C. So, but again, so you put in the suppose, usually there's a definition that you can use there. So then the next part is to flesh out what that definition means for the characters, for the pieces we have involved here. So what does it mean that A divides B? Good, that means A times some integer is going to equal B. What does it mean that A times, or that A divides C? Good, that also means that A times some integer equals C, but make sure, so this is one of those mistakes that she talked about in the second section. Make sure that it's not necessarily the same integer. So I'm not saying that A times K equals B and A times K equals C. So I'm not saying it's the same integer. So one of the common mistakes in a proof is using the same variable when to mean two different possible numbers. But unfortunately, if you use the same variable, then once you start doing the algebra, that variable means the same number each way, each time. So we can't use K in both of these. Because what we're trying to say is a times some integer equals b, and then a times another integer equals c. It could technically be the same, but in general, it's likely going to be different. So we're trying to say a times some other integer equals c. So make sure we want to make sure that we use a different variable for the a dividing into c than we use for a dividing into b. So suppose a, b, and c. So this is my if part. Now I'm going to use that definition to flesh out a divides b and a divides c. So suppose that's where then. So A is going to equal, I'm not even going to use, I'll use two different letters. I won't even use K, but let's say A equals R times B. And A equals, let's do S. And sorry guys, I wrote that backwards. Sort of transposed it. So A times R equals B. And A times S equals C. This looks weird, that's large. And this is all definition of divisibility. All right, so I got the hypothesis supposed, and I've got my definitions kind of fleshed out. Then again, the next thing we usually do is we introduce the construction that we're trying to prove something for. So it's construction we're trying to prove something for is b plus c. So we're going to introduce that construction, and then again, magically, because I have some algebraic definition of a divides b and a divides c, I'm going to start to be able to use substitution to plug things in, and then hopefully use algebra to get to my end state. But let's introduce that construction. So actually, I think I like to use the word so at this part of the proof. So a plus b, or not even that. Okay. B plus c. So b plus c. So I'm going to introduce this construction. But automatically, so b plus c equals, so again, if you notice, if you look back in the example proof we just did, 14 here, and you look back at the proofs we did in 4.2 and even 4.1, once we introduce that construction, as long as the definitions tell me something algebraic about it, I stick an equals there, and I start substituting things in and doing algebra. So b plus c then is going to equal AR plus AS, because that's what my definitions say B and C are. And then it'll be my job from here. Like I said, this is what I always call kind of the meat of the proof. Once you've introduced the construction, it's your job to get from here to the then. A divides B plus C. So we want to think about what our goal is. Our goal is to say A divides B plus C, but to say A divides B plus C, what do I need to say? What's my argument? What do I need to show the reader? Good. I need to show that A times an integer equals B plus C. So that's going to be your goal from here. Is we need to, again, we got some algebra to do, and we want that algebra to bend us towards A times an integer equals B plus C. So let's see if you can get there. Again, we've not only done practice, practice proof in this section, but you've now put together a couple proofs, us as a class, and then gradually you doing more parts of it yourself. So I want to keep doing that. As we keep going, I'm going to gradually have you do more of the proof to begin with, and then we'll put it together as a class and just kind of check what you're getting. Because then when you get to the homework, you're not going to have me to check on a video. You need, it's so I'm trying to graduate you guys into putting together that proof yourself. So anyways, so let's see if you can build the rest of this out. We need to get to A times an integer equals B plus C. So I'll pause and you pause and see what you can put together there. All right, so let's see what you could put together from here. Again, our goal is to say a times an integer equals b plus c. So what did y'all see from there? Oh, good. Hopefully you noticed that we have an a in common. So we basically have an a we can factor out. Not only is it that we have an a we can factor out, but that gets us towards our goal, because if we factor out an a, then we're going to have a times something else. And as long as I can show that something else is an integer, then I've got it. I've got the definition of divisibility. So yes, we can factor out an a, and that'll be, so a times r plus s. And like I said, we have the form we want. We just need to show that r plus s is an integer. So now r plus s, oh man, this can't write well right now. R plus s is an integer. Because the sums of integers are integers, so I'll just say sums of integers there. And notice then that we have it. We have the pieces. We can see that b plus c, as the reader, we can see that it's a times this thing, and this thing is an integer. So then we can say, therefore, a divides b plus c. Again, just definition of divisibility again. Divisibility has 5 i's in it. That is the craziest thing ever. How do you repeat the same vowel so much in one word? It's just weird. All right, good. So definition of, yeah, by definition of divisibility, and we've got it, we've proved it. So again, the beautiful thing about this is that we've proved this in general. So literally we're saying we don't care actually what the integers are, but for all integers where this setup is true, a divides b and a divides c, then a divides the sum of those integers. Carte blanche works for every one of them. So again, the point that I made in the last lecture, I just really want to hone in on that point or make that point again, that the reason we do proofs like this is we show that it works for every combination, every pair where this is true, or triplet in this case. But we show it all in one go. And we show it in general. So we are always going to be showing these things in general. We're never going to be showing these things for specific examples. So pretty much from here on out, I won't say every proof is a for all, but basically almost all the proofs are for alls. So the only time you're ever going to use an example is when you're showing that it's false. So to show a for all statement is false, you just need a counterexample. You're basically proving the negation that there exists. But you just need a counterexample. So that's the only time we're ever going to use actual numbers and as an example is a counterexample to show that it doesn't work. Otherwise, we're going to prove in general that it works for all of the elements, all the combination. Yeah, just all the elements in general. So again, we now know that for anything. So any A, B, and C that you can imagine that fits that scenario, that is now true for. Okay. So let's do another proof. At least probably do, I think we're at least going to do 2 more, but let me get through on this. All right. That won't go there. All right, let's look at 25 next. So let's look at 25. All right, in 25, we're trying to prove for all integers a, b, and c, if a is a factor of c and b is a factor of c, then a times b is a factor of c. So again, the first thing is let's try to retranslate this for ourselves. Put this in informal language. Just what are they really trying to say here? And so take a second and tell me, what do you think they're trying to say? So I think this one just in terms of reading actually is a bit harder, I think, to just try to tell yourself, okay, what are they actually saying here? What they're trying to say, so it's kind of interesting. So again, we have three elements, A, B, and C. And the last one, A divided B and A divided C, but this is a different setup. They're saying A is a factor of C, or A divides C, and B divides C. But instead of trying to prove something about A plus B, well, actually, sorry, about B plus C, well, yeah, this is still a little different last time. So here, A divides C, but then instead of A dividing, say, so A divides C, B divides C. So we got one, so the way you want to think about it is you got one larger number, and we're looking at two factors of that number, two numbers that divide into it. Then the claim is that if you multiply those two numbers together, those two factors, that automatically divides C. So that's essentially what they're trying to say here is if you pick any two factors of an integer, that the product of those two factors also divides the integer. So then the second thing is, again, we go to our intuition, just kind of cycling through arithmetic and algebra that we know in our head. Does this seem true? This is where I really, really wish I had some of you guys live, because actually the fun thing on this is I would go a different direction depending on your feedback here. Because I think that this is one that's not as easy to have an intuition on, or at least it's, so I think some people would say true, some people would say false, and it'd probably be about a 50-50 thing. So I want to see where you guys lean and go with that. But since I can't have you guys respond, so thinking about this, I think naturally I would think, okay, well, maybe this works. So I'm just saying basically if I take one factor of a number and another factor, if I multiply the two, then that should also be a factor. So at least maybe intuitively think about prime factorization, some stuff you've seen before, maybe in an algebra class, that yeah, maybe this works. So let's try this. So for all integers A, B, C, so I'm going to convert this into, again, more of an if then, or just a little more formal writing. So if A divides C, and is it A divides C and B divides C. So on the last problem, it was A divides C and A divides B. That was the difference. But this will be our setup. So A divides C and B divides C. Then AB divides C. Their product divides C. And so my intuition, my first thought is maybe this is true. So let's go try to prove it. And so I would need to start out with my suppose. So suppose A divides C. Let's do the integers. Let's say they're integers first. So suppose A, B, C are integers where So I'm not just saying that this other thing is true, I'm saying that I'm choosing integers that satisfy this other condition, where A divides C and B divides C. Good, so we always start out with our suppose what would be the next stage in this proof. Good, now that I have these conditions, there's a definition there, so let me write out what this means using the definition. So this is gonna mean that what, A times R equals C, and maybe B times S equals C. R and S are integers. I think I actually forgot to write that on the last proof. We should have said that R and S were integers. So now then, so we got to suppose we flesh out our definitions. Then what's the next stage in our proof? Good, we got to introduce our construction. Now, so what we want to introduce here, so the interesting thing here is, so we're trying to show that AB divides C. So in the end, what we actually want is AB times an integer equals C. So our construction is actually C, and C is not a construction. C already exists in this problem, right? So C exists as either AR or BS, depending on which way you want to look at it. So does it seem like we can go, so if I say now C equals, does it seem like I can go any farther? And when I say farther, I mean the direction I want is I need to end up with A times B equals an integer. And does it seem like I can get there from C? So the interesting thing is just in terms of algebra and trying to, trying to make the algebra work, trying to make the construction work, it doesn't actually seem that I can do this. Yeah, it just doesn't seem, I mean, I can see that C equals A times R or B times S, but even if I wrote one of those down, the problem is I can't use any of the rest of this to then substitute something for A or something for R and then keep going from there. And I wouldn't even want to substitute for A because I want A, I just also need a B beside it. But I can't seem to get that to happen. I think another approach that I would see often from students and kind of in grading this stuff is maybe you do that and you're like, well, C doesn't work. So let me just introduce AB, right? Let me throw that in there, because if I can somehow introduce AB and build it up so that I end up with AB times something equals C, then maybe that works. But so one important thing I kind of want to talk about. So if I was gonna introduce this construction, then use substitution, what I'd have to do basically, so mentally we can kind of see A is gonna have to equal C over R, and B is gonna have to equal C over S. So we could do that. We could say this is C over R times C over S. And so you end up getting C squared over R times S. There's a couple issues that kind of happen here. So let me kind of write this down. So AB. There's a couple issues that I want you to remember, both like from algebra and also from arithmetic, that you got to watch out for. So division ends up being a pretty problematic thing to use in proofs. And the reason is because we can't divide by 0. And so I want you to notice the R and the S that we have in the bottom here. Are there any restrictions earlier in the problem saying that they can't be 0? Good, no. On our last section, we called something a rational number, and because it was a rational number, we knew automatically that the bottom, at least when we fleshed it out with the definition, that the bottom of that fraction wasn't zero. And then because of that, we usually would then go later on in the problem and show that the bottom of the construction can't be zero. But these are not rational numbers, these are integers. So one of the problems we run into here is even though I can make a construction here and then we can multiply both sides by RS, so we would end up having AB times RS equals C squared. One of the problems we run into is you can't do this division because you cannot guarantee that the R and the S aren't zero. And in fact, we're assuming that R and S could possibly be any integer, including zero. So because of this, we can't do this move that we would normally do algebraically because we can't guarantee that it's not zero. So I will say in general, unless you're in some problems like with dealing with rational functions where you naturally are using division as part of your, the definition of a rational function uses division. If you're not in one of those problems, you don't want to use division. Because when you've done math before, we've just always sort of assumed that the thing we divided by wasn't zero. And it works practically, at least for our calculations, because practically for those calculations, the context we were in, the domains and ranges we were talking about, it wasn't zero. But even if you think back to algebra, sometimes it was zero and we had to, when you think back to rational functions and algebra, in a college algebra class, you had to make sure that the bottoms weren't zero. And so you would adjust your domain and range to make it so the bottom wasn't zero. Or if your solution that you came up with for your rational equation did make the bottom zero, you would say that there's no solution, right? So even in algebra, we sort of adjusted for the fact that we can't divide by zero. But when we're proving something, there's no calculation to be made. There's no adjustment to be made. The conditions that you're giving for an object are what the conditions are. And so again, that's the problem here. The conditions for R and S are that they are any old integer we could want them to be. But they can't be any old integer because they can't be zero if we're going to be using division in our proof. So unless you're dealing with rational numbers, you should not use division in any of your proofs. Because you could possibly be dividing by zero, which would negate this whole calculation sequence, this whole algebraic sequence that you're running. The other problem, even if you don't remember that, R and S could be zero and you can't divide by zero, the other problem we run into here, so we sort of skate by that, right, by multiplying both sides by RS. But the other problem we run into is that we still have AB times an integer, but not equal to C, but equals C squared. So we don't even have, we can show that AB divides C squared, but we can't show that it divides C from this. And then if we want to be clever algebraically and divide by a C on both sides, the problem again we run into is C is any old integer and it could be zero, and we can't divide by zero. So mathematically, algebraically, we can't do the division that I often see students want to do in a problem like this. So again, I'll give that as a general guide for you guys. Don't use division in problems that don't have division naturally as part of their context, because we can't guarantee that we're not dividing by zero, which you can't do. So that would be a fallacy in your argument. You would have a possibility there. So if I'm a lawyer looking at your argument, arguing against it, I'd be like, well, C could be zero, or RS could be zero, and you couldn't deny that part of the argument. And so I'd say, since one line of your argument has a possible falsehood, your whole argument is bust. And logically, from, again, logical argument standform, I'm correct. That's how lawyers get away with and argue a lot of things out, is they just pick one part of your argument, and if they can they can show that something's possibly false about that, then your whole argument goes. So that's what I would do here. I would say C or RS could possibly be zero. The galley would look at it and say, well, it could be zero. So therefore the prosecutor's argument is null and void. So anyways, so don't use division unless we're talking about rational numbers. Alright, so second issue or bigger issue that we're coming to, so I assumed this was true and I'm working this through. I couldn't come up with a construction for C, and even if I try to be clever and come up with and start with AB and work my way to AB times an integer equals C, it doesn't seem like I'm getting there algebraically. So again, this is a good example of intuitively I thought it was true, but maybe it isn't because I can't seem to get there from running a direct proof. So that's what I'm going to do. I'm going to flip to trying to claim that this is false. And if it's false, I just need a counterexample. I need some A, B, and C where A divides C, B divides C. But when you multiply A and B together, they don't divide C. So I want you guys to then think about that for a second. So I'll just kind of pace the room right here, but take a second and see if you can think of an A, B, and C that is a counterexample to what they're claiming here. All right, so what are you coming up with? So the surprising thing about this is, again, and maybe if you intuitively thought this was true, like I would have intuitively thought this was true if I didn't already know this book and, like know these proofs and have thought through this stuff. But I think initially looking at something like this, I can, if I was in my sophomore, junior year of college, I would have initially thought this was true. So maybe you're like me. So the surprising thing is there's definitely some counterexamples, more than you think. So for instance, so your counterexample may have been different numbers as long as your kind of triplet of numbers works out though. So we can say this is false. It's not really a proof. I mean, it's a proof, but so this is false. And I showed that with a counterexample. So maybe 9 divides 18. 9 divides into 18, and I as the reader can see that 9 times 2 is 18. And 9, or not 9. And 3 divides into 18. That checks. 3 times 6 is 18. But 9 times 3 is 27. And that does not divide into 18. So like I said, the surprising thing here is there's actually a lot of counterexamples that's much easier than you think. You honestly just pretty much just have to think of two factors of a number that when you multiply them are bigger than the number. And kibosh, the claim that they're making definitely doesn't work. So this would be one counterexample, and like I said, there's plenty of them. So this is not true. So again, when you're doing these proofs, just know that she's not going to lead you one way or another. These could be true, these could be false. Let's see if we, not only if I have time, but if we have need for another one. Yeah, let's look at one more. Let's look at 26. So notice that 26 actually is the converse of what we just saw in 25. So part of the reason I wanted to go over these two is, again, just to touch back on this idea of converses, inverses, etc. of an if-then statement. So remember that for an if-then statement, the original and the contrapositive have the same truth value, and the converse and the inverse have the same truth value. But the converse and inverse could have the same truth value as the original, but maybe not. So we just saw that if A divides C and B divides C, then AB doesn't necessarily divide C. So that's false. Notice 26, it's what we're trying to prove here is for all integers A, B, C. They literally wrote this the converse. They wrote it backwards. If AB divides C, then A divides C and B divides C. So this is the converse of 25, which means it could be false like 25 was, but it also could be true because the converse and the original statement are not necessarily tied to each other, truth value wise. So this could be false or this could be true. So this is the converse. Again, let's kind of then, now that we have some experience with 25, trying to like understand what that meant, let's retranslate this. So what are they trying to say here? So here's a little different. Here, what they're trying to say is if I've got two numbers, if the product of two numbers is a factor of C, if it divides C, then each of those two numbers divides C itself. So, or is a factor. So if the product of two numbers is a factor of C, then each of those two numbers separately has to be a factor of C. So I will say, notice that, the problem we ran into, or last time that we saw with the counter example, so the original statement, what we saw with the counter example is these two factors. If you pick these two factors first, you can easily pick two factors that multiply to something bigger than C. But notice when you make the converse, there's a subtle but huge difference. The huge difference is I'm saying that the product already is a factor of C, which means it literally has to be either less than or at least equal to C. It has to be something less than or equal to C. So by making the converse, I've actually fixed the issue that we ran into in the last problem, that multiplying the two numbers could possibly be something bigger than what you're trying to divide into. I've fixed that issue. So I'm saying definitely the product is a factor of C, which means it's less than or equal to C. It's either going to be multiplied by 1 or 2 or 3, some integer, but it's less than or equal to C. So thinking about that, then, if we fix that issue, then should it be true that the two separate factors of A and B, that those also divide C? What do you guys think? And again, it may be 50-50 on this. My instinct is, yes, this should work. It's like last time I was wrong. I thought maybe it worked, but I didn't think about the two numbers multiplying to something bigger than C. But if this time I'm fixing it, I'm rigging the system to begin with that AB is less than C or equal to C, that it's a factor of C, then this should actually work. So let's start with this as true. Let's think maybe this is true. And let's see if we can build the proof from here. So again, I want to phase you guys into building more of this proof before we do it as a class on the board. So I want you guys to start building this proof from here. So you know that there's going to be a suppose part, there's going to be a part with definitions. So I actually basically want you to build those two parts. So all pause and you pause and build those two parts, the suppose part and then the definition part. And then we'll come back and write that out and make sure you got that right. And then we'll talk about the construction part. All right, let's see what you guys got here. So for the suppose part, what did you say? Good, so this should be suppose AB divides C. So just the hypothesis on that if then. Then that the fact that AB divides C, that definition, it tells me something I can write. So what did y'all write there? Oh, also, you know what I missed? I'm sorry. Let's just make that a comma then instead. Say that AB, A, B, and C are integers. So then what you might have said next is something like this, then maybe ABR equals C. R is an integer. And that's definition of divisibility. Five eyes, that is so crazy. All right. Good. So for the supposed part and the kind of fleshing out that definition, you should have had something like that. And again, as long as it includes all those key pieces, all the true pieces there, then you've got it. Good. So then the next part of my proof is I'm going to introduce my construction. Again, notice here that, so our goal is to show A divides into C and B divides into C. So again, we run into a situation where our construction is not something new. We're trying to make some statement about C, basically. So we want to look at a proof like this where in this next part where you usually introduce your new construction, there really isn't a new thing to introduce here. But my goal is to show that A divides C. So A times an integer equals C and B times an integer equals C. So the rest of this proof is then. So I might say something like this. You can say now I'm going to say notice. So again, the key, the crux here as far as like the meat of the rest of this proof is again that we would normally introduce a construction, but we don't have to introduce anything. We already know what C is. We're trying to say two different things about C, that C is A times an integer and C is B times an integer. But we already have C. Once I wrote this out, I know what C is. So what I'm going to do is I'm just going to say notice, so C equals, we say ABR, so I can just highlight the fact that that's A times BR. And BR looks suspiciously like an integer. Also, I'm gonna repeat it, and this time I want you to notice that I can rewrite this as C equals B times AR. And AR looks suspiciously like an integer as well. So this is a good example of a problem where you don't necessarily introduce something new, and you don't have to do a bunch of substitution, but what you do is just some clever algebra. You show the reader that, because again, the rub here is you already have C, and if I look at C, C is in fact A times an integer and B times an integer. So I just need to highlight that to the reader. And I use some algebra, some clever algebra, to do that, basically associative property and commutative property. But notice that we do seem to have this. A times BR is C, and B times AR is C. So then what would I say? What do I need to say again about BR and AR to kind of finish off my definition of divisibility in both cases? Good, so I need to say that they're integers. But suppose, then notice, and then I might just say something like this. Now, BR and AR are integers. And this is because products of integers are integers. Then I can go from there, then I have it. So this line says C equals A times an integer, this line says C equals B times an integer. So therefore, A divides C and B divides C. And again, this is definition of divisibility. And we've got it, we've got the proof. So in fact, in general, this does work. If I think of some number that divides C and I think of the factors of those numbers, those automatically have to divide C. Because this number is already less than or equal to C, and those factors then are definitely less than or equal to that. Good, but this shows it in general, so this works always. Think of a pair A, B, and C that fits this condition, and it automatically works. Good. All right, so that'll be it for 4.4. That kind of covers some of the proofs you guys are going to see, just the work and the proofs that you guys are going to see, and that'll be good for this week. So go ahead. Again, I know some weeks are going to be like this as far as if giving tests in another class. It just takes time, and so it makes it hard. I usually make these videos on Monday and Tuesday after all my classes and all my work. But this Monday and Tuesday I ended up staying in the office till 7 working on those tests for the other classes. So there'll just be a couple weeks like this, and I'm sorry about that, but just kind of the logistics are what they are. So go ahead and knock out the homework, and I will see you guys next week for, I think we're gonna do 4.7 and 4.10. All right.